So if you remember, here is a formula that we have used in the past to describe compound interest. And if you remember, this U0 is an initial investment. I is our interest rate per compounding period, and N is the number of those compounding periods. And UN is just what we get out at the end of that time. So just to help us to understand this very quickly, let's just make up a very quick example, and then we'll use this and expand on this to help us think about what E is and why it's important. So suppose we had $1,000 and we invested it for 1 year at 6% interest per year. All right, PA, per annum. All right, okay, so let's just think about that, right? Okay, well, if I was going to be doing that, this is a really nice, simple example. We would calculate 1,000 multiplied by 1.06, and that's it, because it's the power of 1, right? Okay, no big deal, really, really simple. But what would happen if we started to compound it, not yearly, but in smaller and smaller time increments? So, for example, what would happen if we started off by saying, well, okay, N is 4, right? So we're doing this quarterly. Every quarter of a year, we're going to work out and compound that interest, which means recalculate and recalculate. Well, if N was 4, then what would happen is we would still have our 1,000. We would be multiplying, though, by 1 plus, well, that's 6% divided by 4. Let's write it as a percentage like that, look, to the power of 4. And when I'm writing that 6%, what I really mean there is I'm doing 1,000 multiplied by 1 plus 0.06 over 4 to the power of 4. And if I was to calculate that, well, we would come out with something like this, 1,061.36. Okay. Great stuff. So, and now let's go back again. What if we now, rather than did it per quarter, we compounded per month? So in this year-long period, we were compounding the interest 12 times, recalculating every month what the new interest would be, adding on and so on through the 12 months. Well, if that was the case, we would have 1,000 multiplied by 1 plus that 6% over 12 to the power of 12, right? We'd have a smaller kind of percentage per month, but we'd be doing it 12 times. And if we calculated that, it would come out at 1061.68. Notice how close it is to the previous calculation. The difference there is the interest on the interest, if you like. And okay, well, let's go back and then carry on again, and let's continue thinking about this. Well, what if instead of doing it per month or per quarter, we did it every single day? So that means that we were working out interest daily. So N is 365. Well, we could do that, couldn't we? I guess that would be 1,000 times 1 plus 6% divided by 365 to the power of 365. And if we were to calculate that, we would get 1061.83. Again, not much of a change. And of course, we could go even further. I mean, let's do one more. Let's imagine that we calculated interest every second, right? Every single second of the year, we were recalculating. Well, if you did 365 times 24 times 60 times 60, you would have 525,600. So if we were to calculate it then, we would have 1,000 times 1 plus 6% over 525,600, all to the power of 525,600. And if you were to calculate it, it would come out at 1061.84. Only, 100th of a decimal place, I guess, or 1 cent difference from doing it 365 times in a year. So what we're going to aim for, though, is rather than even think of n being a particular value, what if we calculated interest consistently and continuously all the time? So what we're going to be thinking of, let's say that, okay, our n value is going to be very, very large. N is going to tend towards infinity. Okay, so here is the formula for compound interest. Let's make a few changes to this. Let's see if we can use what we were just doing to improve this and draw out E for this continuous growth. So, first of all, we should know what these all mean already, but let's make a couple of changes. So, first of all, let's say that I is equal to R over N. And we'll say that R is the interest rate per year, and N is the number of payments per year. Okay, and that's just what we were doing before, right? We're taking that 6%, wasn't it, that R value, dividing by different values of capital N, number of payments per year. So we'll make that swap in just a second. Another thing I want to do is, okay, then, well, our n, our lowercase n in our original formula, we've just changed capital N to be the number of payments per year. So let's say that n is going to be the number of payments per year multiplied by t, where t is the number of years. There we go. So now we can do some swapping around and some rearranging and hopefully make our formula a little better. So let's try again. So we're going to have un is equal to u0, 1 plus r over capital N, all to the power of nt. Now, that is what's just been going on, I suppose, with the difference here being maybe that t is variable. We had it set at 1 year, but t could be more now if we wanted it to be. This still isn't going to help us to really draw out what this bracket is going to be, because really we're looking to consider this as n tends towards infinity, right? That's okay. We want that number we're dividing by to be massive. As you saw, it was 1, then it was 4, then it was 12, then it was 365. Okay, we want that to see. We want to have this continuous, so it's tending towards infinity. Now, to help us to do this, we'll make yet another substitution to draw out the math here. Let's say that a new variable, is going to be capital N over R. Okay, so if we just swap this around a little bit, then what we're going to have is un is equal to u0, and then we are going to have 1 plus 1 over a, because it's n over r, not r over a. And actually, we can even get an a out of the power there. So we could write this as a to the power of rt. And if you check the math there, n over r to the power of rt, well, the r's are going to cancel. We're just left with the nt we had in the first place. Now, my reason for writing this is because, okay, if n is tending towards infinity, then actually we can now say that a is the thing that's tending towards infinity. So what happens to this as that takes place, right? So as now a tends towards infinity, what is going to happen to 1 plus 1 over a to the power of a? I think we should just start thinking about that now. Let's put some numbers in and see what happens, because this is the thing that we need to consider that is really affecting all of these numbers. So, okay, so if we start with a, and 1 plus 1 over a to the power of a over here, if we put into that a is 10, then we are going to end up with, well, 1.1 to the power of 10, which is 2.594. If we increase this on a little bit, let's just imagine we've got a is 1,000. Well, we'd have 1.0 0.01 to the power of 1,000 there. And this is 717. If we go a little bit further than that, maybe to 10,000, well, if we work that out, we would have 2.718. And then if we go to 100,000, this would come out if we inputted it in again, 2.718. So as a gets massive and is tending towards infinity, 1 plus 1 over a to the power of a is tending towards this number, 2.718. And this is E. So actually, our formula then for continuous growth is going to be UN equals U0, some initial investment, E RT. There we go. And E is the number that makes this work, right? R is our annual percentage. T is the number of years. U0 is that initial amount. Okay, this is it. So if we were increasing compoundly, let's just say we had an initial investment of 1,000 and we invested it for 4 years, and let's keep that 6% there. What we would have to do is 1,000 times e to the power of, well, 0.06 times 4, and that is going to get us our amount, 1271, I believe that is. That is if we are having this continuous compounding all the time. And so that's what E is. That's why it's useful, at least one way of thinking about it anyway. It has lots of other applications all over mathematics.